We shall start with deep drilling fields discussion.
Okay, hopefully you can see the slides and hear me.
Yes, we can.
Excellent. Okay, so yes, thank you to Željko and the SCOC and the organizers for having these community sessions. And of course, thank you also to Lynn and Peter and everyone else doing all the hard work. Yeah, certainly the idea behind these community sessions are topics that will appeal to a broad range of science interests in using Rubin. And so this session was put together by Desk, TVS, AGN, and Galaxies, and so focused on the deep drilling fields. So the way we have organized this session is, so first we'll have a few short presentations. First by Peter, just reminding us what the plan is for the DDFs in the current baseline. Then we'll have brief presentations, 2 slides or 2 slides-ish, twiddle 2 slides. There are some question marks here, but those have been filled in. I forgot to update this slide. With presentations from Desk, TVS, AGN, and Galaxies about their science interests in the deep drilling fields, and then how that informs the observing strategy. And then after that, I'd like to have an open discussion from all science collaborations, anyone here, about ideas for what should be the baseline DDF that's implemented as the baseline as we go in terms of the observing strategy for the DDFs. And then what other simulations are needed, what variations in that strategy we can recommend that the SCOC recommend are explored going forward. So that's the idea. So I think we can start with Peter's slides. Peter, do you want to control the screen, or do you want me to advance?
You can go ahead and flip it. That's fine.
Sure. All right. So I think this is the first one.
Yeah. So just a brief introduction to the deep drilling fields. There's very little requirements on the deep drilling fields. I think the science requirement document just says they should be about a magnitude deeper than the Wide-Fast Deep survey. And so here are just 2 plots. One where I'm showing the coadded depth of the Cosmos field, and then down below is an image of the Euclid double field. So we've got 4 official fields. There's the names of them, and then the unofficial final field is Euclid, which we've split into 2. So it's the same total number of visits as the other fields, but split into 2. And you can see the Euclid footprint in red around there, and then that double field. So those are the deep drilling fields. Go ahead and give me the next slide. And on the footprint, you can see the 5 spots where they are. They are kind of concentrated in a narrow right ascension range, which makes things a little bit difficult because then we start to get oversubscribed on that spot of the sky. But it's not too bad. Our current, another thing to note is that at any given time, only 5 filters are loaded in Rubin. So we can't do a sequence of all six filters because we don't have all of them loaded at a time. The current sequence is to take 8 U exposures, all a total of 30 seconds, 20, 30 seconds in R, 20, 30 seconds in G, 20 in I, 26 in Z, and 10 in Y, of whichever 5 of those filters happen to be loaded. We've been dithering nightly to fill in chip gaps. We could do within a night if that was something people wanted to do. Also, I'm not sure how precise we're going to be returning after filter swaps, so there might be some jitter in there as well. We also set the camera rotator angle randomly per night, so there's lots of dithering going on there. We're not going to finalize the dither size until we have on sky data, and I think at least one of the fields has a bright star nearby, so we might want to make sure we're dithering always away from the bright star and not necessarily doing a completely random dither. Next slide. So here's our current criteria for when we execute a deep drilling field observation. It just has to be not during twilight. There's been enough time to complete a sequence before twilight or another scheduled observation happens. The moon has to be down. The field has to be at a reasonable hour angle, so it's not a very high air mass. The deep drilling field has to have not exceeded its limit. Each DDF currently gets about 1% of the total visits. And it has to have been a while since the DDF executed. Usually we say 1.5 days. If something has fallen behind, we'll let it go, just a half day before we repeat it. And I'll point out this was just, a very simple, bunch of if statements in Python to get it to execute about right. I don't think this is how we should execute the DDFs in operation. I think for the drilling fields, it makes sense to pre-compute good times to execute them and just feed that list of pre-computed times to the scheduler and let it try to execute then. So go ahead and go to the next slide. And so these recycled slides from yesterday, I've started working with the Jarobi optimizer, and you can see here the 5 sigma depth as a function of time for one of the deep drilling fields, and then the points are where Jarobi says these would be good times to execute the deep drilling field, where I've tried to keep it as, I told Jarobi, okay, there's a depth limit, air mass limit, and I want to keep some downtime limits, and I want to keep the observations as uniform as possible with those constraints. And you can see it does a pretty good job. It keeps things at as deep as possible, and then it does a good job saying, okay, there's a gap caused by the moon, so I do have to go when conditions aren't pristine to make sure I stay as uniform as possible. So next slide. And here's just that curve where I'm saying I input a desired cumulative number of events, and then the scheduler is able to match that incredibly well. So the only extra thing we need to add in here still is some logic for if a deep drilling field fails to execute because of weather or something. How are we going to make that up? Do we want to just schedule many more deep drilling sequences than we think will happen, and if weather knocks it out, that's fine, or do we want to reschedule it when it gets failed? And there's a question from Harry. So right now we're not taking deep drilling fields during moon time, during bright time. There's a requirement that the moon be down. So that's how we're solving taking thing, and that's how we're solving the bright time problem. We could adjust the exposure times if we wanted to, if we wanted to maintain the cadence and get deep drilling fields when the moon is up. But usually we just wait for the time of night when the moon is. We don't take observations at full moon, and then as the moon wanes, we'll wait for it to set before hitting the deep drilling field. And Jelko asks, the code can support different strategies for different DDFs? Absolutely. My plan would be to make a script for each deep drilling field and just list out all the times we want each one, so each one could be solved independently.
Can I just interrupt 1 second? I forgot to mention before, we also created a channel on Slack called #DDF. So it might be good to capture some of these questions and ask them there, and I'll try and monitor things as well. I had the same question. I didn't realize the moon had to actually be down as opposed to just far away. So that's interesting.
Right. Yeah. Right now we've got it just as a hard. The moon must be down. But again, that's our current logic that I'd like to throw out completely. Again, that's all I have to say about it. Happy to answer any other questions or move on or whatever.
Okay, great. Thank you very much, Peter. Any questions? We have time built in for questions and discussion, so it's perfect time to ask Peter things right now, and we'll continue. I don't see any.
Well, I'll
Yeah, go ahead.
ask right now on the baseline, the DDFs are just sort of happening spread out over the whole 10 years, I assume.
Yep. Yeah, they're kind of uniform throughout the 10 years.
And then, Peter, you said, the requirement is that 1 magnitude deeper. In the baseline, how much deeper do we actually get?
It's a good question. I don't know off the top of my head how much deeper we're getting. I can look that up and have it in 2 minutes.
So, one idea which we may come back to later is the idea of this, and it's mentioned here, rolling fields where we move a little bit the fields, and the question is whether we can still do that and get 1 magnitude deeper in a larger region or not. So it'd be good to know what the limitations there are.
So here, when I say rolling, I'm meaning the idea is that we would keep the positions the same, but for example, do double cadence on one deep drilling field in a season, zero cadence on another one, and then swap it the next year. So static science wouldn't be impacted, but you would have a season of, say, double cadence on a deep drilling field. We can do spatial as well.
Yeah, and then and in relation to Angelica's question, this idea of, I think it's the Cosmos field that's off in a different RA. There we might imagine some different strategy because that's the only one available. So, higher cadence when that is available, and then lower cadence for the other 4 when they are available. Something like that might be interesting to explore.
Yes, if the baseline keeps maintain one magnitude depth deeper. I don't think so. I think it will build up to it. It should be, but both the wide, fast, deep and the deep drilling fields are currently both executing linearly. That's the way to put that. They both have cumulative curves that look like the plot. So I'm not sure how much deeper it will be after 1 year.
Okay, any more questions for Peter? And I think, Peter, I mean, correct me if I'm wrong, but the idea is that, right now there is quite a lot of flexibility in the deep DDF observing strategy. That's a part of the motivation for this session. So it's, today is not going to be the end all and be all of this discussion. Let's continue, questions like this and discussion, especially on Slack, for example. Yeah,
in the next week or two, I'm going to be going back to the white papers and the cadence notes and starting to code up the experiments because that was one of the things that got put off. So very shortly, we should have more DDF experiments, and this is the time to bring up other ones that people might want to execute.
Great. So on that note, now let's move over to the science collaborations. And first up is Philippe, who's going to talk about desk science and observing strategy recommendations for DDFs.
Hi, so my name is Philippe Gris from IN2P3 in France. So I'm going to show a couple of slides of work that has been done with Nicolas Regnault, and it's about the interplay between the DDF observing strategy and the supernovae science. So the DDF mini survey is probably critical for the success of the supernovae science in LSST.
Sorry, if you're not Philippe, could you please mute?
I'm being a diligent.
I think we're good to continue.
I do not see the slide anymore, but
it looks like we lost shared slides. Who was sharing, Saurabh or?
Okay.
There we go.
Okay, so success meaning here that we want to perform precise cosmological measurements. We usually do that or extract the cosmological parameter using a Hubble diagram. And you have an illustration on the left of this slide. That is a distance modulus as a function of the redshift. And all the points that you have on this slide correspond to supernovae, and the black curve is a fit so as to extract the cosmological parameters. And you have also on this plot 2 redshift range corresponding for the supernovae to the WFD fields, survey, typically between 0.01 up to 0.5, 4.5, and the LSST, and for the LSST deep drilling mini survey, then we would have something between 0.3 and 1. So if we want to probe higher redshifts, we need to use the DD mini survey. So when you minimize this chi-square to extract the cosmological parameter, you have, of course, in the game, the covariance matrix with the errors, and optimal cosmological constraints means minimizing the uncertainties. And there are 2 uncertainties that you want to be as low as possible in some sense. The error on the distance modulus, which we typically take as lower as 0.12, so as to be lower than the interesting dispersion of the supernovae. And of course, the systematics uncertainty that you want to minimize. And one of them that may be dominant during LSST would be the cosmological mean increase bias. But since these parameters are extracted from the photometric light curve, this induces 2 types of requirements, one coming from the supernovae, that you want to observe the large sample of well-measured type 1a supernovae up to high redshift completeness. And the other is coming from the observing strategy, because the quality of the light curve will depend on the way the observing strategy will be made. And among the parameters that are important to get high quality light curves, the number of visits per band and per night, the cadence of observation, the number of season lengths, the number of fields, the time budget, the number of seasons of observation, and so on and so forth. So the next slide, please. So from the supernovae requirements, we can have two natural, in some sense, metric to assess observing strategy. One in the number of supernovae, of well-measured supernovae up to a given redshift completeness, and the other the redshift completeness. And you have on the left plot, on the left side of this transparency plot, corresponding to an assessment of the some of the DDF simulated strategy by LSST. I think it's FBS 1.5 simulations. And as you can see, there are quite some differences between the observing strategies. Some strategies have a high redshift completeness, but a low number of supernovae. Some have a low redshift completeness, but a high number of supernovae. And other, which is called labeled DDF underscore heavy here, had a large redshift completeness and a large number of supernovae. The thing is that DDF heavy was done, but with a high DD budget at the level of 12%, if I remember well, and all others were with a budget of 5%. So the conclusion is that it's difficult to go beyond a completeness redshift of 0.65 with a budget of 5%. We also saw large internet gaps in the simulation, more than 10 days for some of them, and it's really harmful for supernovae. We can lose up to 30% of the total number of supernovae, and this is due to the fact that the sampling, when you have a large internet gap, is not good. And if the sampling is not good, the distance measurement that we extract from the light curve is not accurate enough to integrate the supernovae in the Hubble diagram. There are also some irregular median cadences, no uniformity between season and fields. And finally, for what concerns the translational dithering, we've shown that there was an impact for low cadences. Low cadences here meaning cadences bigger than 3 days. So the first question is, can we go higher in redshift completeness? And if we want to go higher in redshift completeness, we need to increase the number of visits per observing night. And this is due to the fact that the redshift completeness value is more or less ruled by the error, the error that we impose on the error on the distance modulus, 0.12. And this distance modulus error depends on the signal-to-noise ratio per band, which depends on the 5 sigma depths per band, which depends on the number of visits per band. So you have a link between the redshift completeness and the number of visits per band. And you have an illustration on the right plot on this slide, which is the number of visits that are required to reach a given redshift completeness. And you have an illustration to reach 0.8. And in that case, you need 121 visits per observing night. With this specific number of visits per band, 2 for the G, 9 for the R, 45 for the I, and 64 for the Z, and 11 for the Y, and for the cadence of 1 day. With this, we are able to optimize observing strategy for supernovae, type 1a supernovae cosmology. Using these two metrics, number of well-sampled supernovae and redshift completeness, there are two possibilities. Either we tend to optimize the number of well-measured supernovae, but in that case, since the time budget is limited, you cannot go to a high redshift completeness. This is what we call in the following the deep universal survey, or we can choose to optimize the redshift completeness to go to higher redshift completeness. But in that case, because of the time budget, we cannot have a high number of well-sampled supernovae, and this is the deep rolling survey. So next slide, please. So to give you a little bit more detail about these two strategies. So on the left, the deep universal survey. In that case, all the fields are observed for 10 years with the same cadence to 3 days, the same season lengths, 180 days max, and the same redshift completeness, which means the same number of visits per observing night. And on the right, the deep rolling survey. In that case, the fields are observed at least 2 years each. The cadence is of 1 day with 1 field per night and per season. And there are 2 types of fields, 2 ultra-deep fields up to redshift completeness of about 0.8. And this, if it is optimal, this should be the northernmost field, that is Cosmos and XMM-LSS. And then you have 3 deep fields with a completeness redshift of at least 0.6. The plot that you have on this slide correspond to the performance of these 2 surveys. In the y-axis, for each of the plots, you have the redshift completeness, and the x-axis is the number of deep fields. The black curve corresponds to the budget, depending on the configuration that you will have. And the red curve, the red dotted curve corresponds to either the, on the left, the error on the W parameter, or on the right, the number of well-sampled supernovae. And if you compare these 2 kind of plots, then the conclusion is that it will be difficult to measure the W parameter with an accuracy better than 2% if the budget is lower than 5%. There seems to be a promising scenario, which is a deep rolling survey with a budget of about 8%. And this is what corresponds to the blue points on the left 2 plots, on the right 2 plots, sorry. For what concerns the error on the W parameter, this would be between 1.3 and 1.4%, and the number of supernovae would be at the level of 3,000. And what we found important during these studies is to have a deterministic scheduler or survey, so as to have, in particular, a budget or gap recovery mechanism that should run daily, so as to keep and to have a high quality survey for the supernovae science. A paper summarizing all these studies is in preparation. It is in internal review in desk now and should come out soon. And I think I'm done. Thank you.
Great. Thank you, Philippe. Any questions? I'm trying to keep an eye on the time as well, so we'll limit the questions a little bit here. Meg, go ahead.
So wearing my SAOC member hat, 8% is not 5%. So given we have to sort of evenly distribute the unhappiness, where would desk want to take out that time to add to get 8%? Is there something within the wide fast heap or within their sort of recommendations or others, science areas, et cetera, to get back that several percent you need to do the rolling? Is there, you know, because you've also asked, like, as every other, it's all trade-offs in between. And so I'm wondering, is there something on the lower redshifts sort of requirements that could be relaxed to help find that time to get you to 8%? Maybe the answer is no, but I was just wondering if there's some consensus within desk of, if there's no more time to give, where would you take that from?
So that's a tricky point. I think that for the WFD, it will depend on how well the rolling cadence is working. I mean, if the rolling cadence is performing well, in that case, we could imagine to lower the number of, well, we could imagine to find some time, I mean, in the WFD for what concerns the supernovae, and to spare some time for the DDFs.
Harry?
So I was just wondering, it's partly along the same lines. You know, if you were just optimizing for supernovae, I guess I could sort of imagine you might optimize in one band and give up colors and just get fewer epochs in the colors because they're mostly just to identify, right?
I'm not sure I understand the question, because
when we are
optimizing,
get a light curve, a single band, you know, let's say I or Z band light curve, and get fewer epochs on colors, just because there you're just trying to find out what kind of supernova it is. You don't necessarily need the multi-band light curves quite as much. Maybe I'm wrong.
So in this study here, we request at least 3 bands for the measurements. And it is mandatory for the quality of the supernovae that we are requesting.
In fact, the uncertainty in the color is the dominant component in the uncertainty in the distance.
Yes.
So it's not actually the time sampling, it's the getting really accurate colors, especially near peak. That really helps with the distances. So yeah. Yeah, so if desk supernovae wanted to do it all, we would only choose 3 filters and get higher depth in just 3 filters rather than the whole thing, so maybe that's another answer to Meg's question. The filter balance could also be looked at as well. I think Eric had a comment, hopefully quick given the time.
I withdraw.
Okay, thanks. Okay, in the interest of time, let's continue. So I think next up is TVS, and Rachel was going to present these slides.
Thank you. So TVS has made 3 main proposals for deep drilling fields, which I'd like to focus on, though I wanted to emphasize that, of course, we are also interested in supernovae science. So everything that was just presented is of interest as well. So to focus on TVS's particular input then, since our science is inherently time domain, we're understandably concerned that periodic signals can be recovered accurately without aliasing for stars that are within the deep drilling fields. So that will enable a range of science, from understanding stellar pulsation and interiors to getting the physical properties of stars from binaries. Determining the periods of auroral rays as well is important for galactic structure studies. So we're therefore advocating that the time sampling of intensive deep drilling field observations could be optimized to avoid regular sampling in time and therefore break down the aliasing in the light curves. And that would apply to all of the deep drilling fields that are selected. Next slide, please. So TVS did propose some new deep drilling fields, one of which was to be located in the Galactic bulge. The goal in this case was to complement observations of that region, which are going to be performed by the Roman mission contemporaneously with Rubin. Now, Roman will observe much more intensively than Rubin, with a cadence of up to 15 minutes, but its observing strategy will be heavily seasonal. And their intensive observation periods only last for 72 days, followed by gaps of many months. So Rubin can significantly increase the science returned from this survey just by filling in those gaps with regular monitoring of that region, which is smaller than a single Rubin pointing. But in addition to that, if Rubin is able to observe that field on the same nights as Roman is observing it, then the combined data can also be used to measure the masses of free-floating planets discovered by microlensing within that field, which would be difficult or impossible to constrain any other way. So in terms of scheduling, baseline version 2.0 increases the coverage of the galactic bulge, which suggests that the long-term monitoring of this field may be provided by the wide fast deep. And if a rolling cadence strategy is used, then that will be true only in years where the Roman and Rubin surveys coincide. So we advocate for some careful coordination with the Roman survey on that. Near simultaneous observations, on the other hand, are probably going to be more difficult to schedule, but it's not impossible that that could be done with sufficient coordination as well. Next slide, please. TVS also proposed a set of deep drilling fields to be located over several major star-forming regions. The scientific driver in this work is to measure stellar activity cycles, as well as mass accretion, and detect transient events such as flares and outbursts, all of which will help us to understand the star-formating process. This requires relatively intensive observations of given star-forming regions for a limited period of time. And we wanted to stress that the proposed observing strategy actually repeats those observations on an annual basis in order to achieve the science goals. So the proposal wasn't just for a single star-forming region, which it may have been interpreted as in the past. It actually focuses on several, and that potentially raises potential complexity in the observing strategy if it were to be integrated with either the wide-fast deep or the a mini survey of the galactic plane. And we feel that it would be good to resolve that earlier than phase 2. And that's all I wanted to wrap up with. Thank you very much.
Thanks, Rachel. Any questions? I see there's one from Jelko in the chat. Rachel, can you see that, or do you want me to read it?
I can. The bulge observations are effectively guaranteed, yes. It is one, the Roman exoplanet Galactic survey is one of the two primary surveys for the Roman mission, the other being a low extinction region survey. And the exact details of the observing strategy will be finalized anon, but the fact that they will dedicate time to that survey is guaranteed, yeah.
Thank you.
Other questions for Rachel? Okay, let's move on. I think AGN are next. Neil?
Hi. Yes, so I'd like to talk about AGN science in the deep drilling fields. We have a couple of driving science goals here. We're clearly very interested in using the fantastic Rubin data to just select active galaxies based on colors, variability, lack of proper motion, and so on. We expect to be able to detect 20,000 or so AGNs per deep drilling field. So we'll have very powerful statistical samples. We'd like to use these to investigate demographics, to study AGN evolution, particularly out at high redshifts and faint magnitudes, where Rubin is providing a unique window. We are also interested in exploring AGN physical processes using multi-wavelength data, for example. And we're also interested in investigating the coevolution of supermassive black holes and their host galaxies. Again, that will be combining Rubin with the fantastic multi-wavelength data that are in these fields. One particular strong area of interest is studies of AGN variability. For example, you can use just the Rubin data largely by themselves to investigate accretion disk reverberation mapping, measuring directly the sizes of AGN accretion disks from reverberation lags, just using the continuum bands. And we should be able to do this over a wide range of redshifts and luminosities with large samples to learn how AGN accretion disks have evolved over cosmic time. We also have a lot of interest in using the Rubin data as a photometric support for spectroscopic reverberation mapping studies, where here we're measuring the size of AGN line emitting regions, and we can use this information to derive supermassive black hole masses. We're also interested in testing general AGN variability models, and then we're interested in exceptional examples of AGN variability. For example, due to close binary supermassive black holes, there have been some candidates for such systems put forward. We'd like to investigate such things further. And then, of course, we're interested in transient supermassive black hole phenomena, including things like stellar tidal disruptions, AGN changing look events, flares of blazars and other AGNs, and so on. So we have a broad range of science here. Next slide, please. Yes, and so we had a couple of main requirements that we've put forward. One thing is we're very interested in making sure that the footprints for the deep drilling fields are done right. And a couple of points there. Well, first, we certainly want to maintain at least the 4 original deep drilling fields with aggressive investments of time. I'll say more about that in detail in just a minute. And we're also, of course, very happy if the Euclid field is added. We'd like to make sure that the central pointing directions are chosen well to align with the superb multi-wavelength data, which have been gathered often with Rubin in mind, where there have been enormous investments. And so we've provided advice back in our 2018 white paper of exactly what the central pointing position should be. And we'd also would like to keep the dithers reasonably small so that you're not dithering off where the superb multi-wavelength data are. And then regarding the cadence, we have a number of important points there in line with our strong interest in variability. One thing we definitely want is to have long seasons for all 10 years of Rubin operations. We don't want Rubin to skip a year on one of the deep drilling fields or something like that. And we want the seasons to be as long as reasonably possible, with at least sampling every 4 to 5 nights. Now, you can sample more densely than that if you wish, but this is kind of a minimum requirement. We also then would like at least 4 years of the 10 to have periods of very dense sampling. And this is to enable the accretion disk reverberation mapping where the lags are known to be quite short. There we're talking about sampling like every 1 to 2 nights to the extent that weather allows. And we've shown with simulations that you should be able to do successful AGN accretion disk reverberation mapping if you have sufficiently dense sampling for sufficiently long periods of time. In terms of our filter balance, we suggest a visit pattern in UGRIZY. It goes like 4, 1, 1, 3, 5, 4. But the U band, of course, will not be fully cadenced in there. We understand, but that's the kind of filter balance that we would like to accomplish the science I've described. And of course, here we're also, of course, interested in getting fairly uniform depth for good photometric redshifts. We also suggest in our recently submitted cadence note to consider what we call accordion cadences. The idea here is that you could have these very dense sampling periods that I've described in the central parts of each season where the air mass tends to be low, and that can help to ensure you achieve very good photometric depths while also getting good time domain coverage. We also would like, as has been mentioned previously, to minimize the nightly effects of lunar sky brightness by scheduling observations strategically in that respect. And then we would also like to coordinate constructively with other time domain efforts. I've mentioned, for example, that there's ongoing spectroscopic reverberation mapping in these fields. We'd like to make sure that that these projects are talking to each other. And we also are interested in appropriate cadencing coordination with Roman and Euclid and other facilities. And we have worked out the total cost of our plan for such a cadence. We can do this in about the 5% that has been indicated might be what the threshold would be. And these requirements on the cadence should be kind of interpreted as our minimum requirements. You can go beyond these, adding in additional observational epochs to accommodate supernova goals, to accommodate sampling a wide variety of timescales to break degeneracies with periodic stars and so on. But these are kind of requirements that we need as minimum ones for AGNs. And I will just end with my next slide, saying that we've actually put a fair amount of work into this over the years. This over here is on the left is the 2018 white paper, which is available on arXiv. You can see the arXiv link there. And then to follow up on that, we have just recently submitted a cadence note where we essentially elaborate on the things we said in 2018. We actually are standing pretty well by the things that we wanted back in 2018, although we offer a few improvements and tweaks in this cadence note. So that's our desired science and our observation requirements. Thanks.
Thanks, Neil. Any questions? Yeah, Knut?
Yeah, so looking over the list on the previous slide, I mean, they don't really read like requirements, right? That if these things aren't met, then the science fails. There are. I mean, I think there are things that you would really like to do the science, but I think in order to be able to evaluate whether something is useful for AGN and the DDFs, it would be good to kind of separate out the things that are true requirements from the things that are nice to have.
Sure. Okay. Well, so just quickly, I don't want to burn a lot of time, but the long seasons are a requirement. With that 4 to 5 night sampling, I would think of that as a pretty good requirement. And again, this is all fleshed out in the cadence note and the white paper that we've published. The 4 years with dense 1 to 2 night sampling periods is a requirement. If you don't do that, you're going to lose the accretion disk reverberation lags, for example. This filter balance, well, something like that is a requirement for our science. You need that kind of a broad filter balance to do the accretion disk reverberation mapping, for example. Now, the accordion cadences, that's not a strict requirement. In fact, back in our 2018 white paper, we in fact, suggested a fairly uniform cadence over all 10 years, but that turned out to be very observationally expensive. And so here we're kind of offering a way to reduce costs while still maintaining a lot of the exciting time domain science, and also keeping the photometric depths. But so that one is not strictly a requirement, but it's our attempt to be accommodating of the needs of what other science collaborations might have. And so I guess I don't want to burn too much time. I'm happy to chat with you, Newt, offline about that further. There's definitely are some requirements in there. And again, check out the white paper if you're interested in more details.
Thanks. I also suggest not just offline conversation, but the DDF channel, which I will keep plugging so that people can follow along. Eric?
Yep.
Sure. Thanks, Neil, for going through all of this. You noticed that you have the 4 original DDFs as a requirement/request, and you mentioned being happy about the Euclid Deep Field South joining that. I'm wondering for AGN science, is it important that the Euclid Deep Field South in this sort of half the exposure time over a figure-8 shape get the full 10 years of DDF? Or since the depths would still match Euclid well, would it be okay if that were just a deep drilling field for a few years until Euclid is done taking data?
Yeah, so clearly it would be nice to have that sampled in a similar way, to just add to the numbers. But we do think, that the numbers that of AGNs that we're going to have will be very good, just with the 4 original deep drilling fields that I've been plugging for I don't know 15 years now or something. And so our thinking has been, let's make sure that those 4 get done well. That will let us get our science done. If you want to do Euclid, great. If you're willing to do it in a way that's accommodating of AGN science, that's also great. The multi-wavelength data, at least at present, is not laid down as well in the Euclid Deep Field South. There is some stuff, from the Akari Deep Field South planning stuff, but it's not at the same level as the other deep drilling fields. And the AGNs are just such multi-wavelength creatures that you really do need that at some significant level. Now, one could imagine going in, trying to build up that field in a multi-wavelength way, but one might find this to be challenging because panels may tend to say, look, you already have 4, with these huge investments of observational time, convince me that we really have to spend another 2 million seconds of XMM time to go cover another one. I'd love to go do it. I'll be happy to try to write a proposal, but I'm not clear that proposal would be well received. Yeah.
Okay, I think we still have one more science collaboration to get to, and we're almost running out of time for the session. So thank you, Neil, and please let's follow up on Slack. So and last but not least is Galaxies and Benny. You want to go ahead?
Hi, I tried to update this, but so hi, I'm Ben Holverda, the Galaxy Science Objectives. So we talked about the deep drilling fields, especially about for extragalactic science is going to be a huge opportunity, precisely because we have that multi-wavelength data that tells you everything about galaxies. So part of the things, whether or not it's a requirement or a nice to have, get one of the deep drilling fields up to the 10-year depth early in the survey, so we can actually see how well we do. Does it integrate all the way down? Do you get to the lower sulfur brightnesses? We don't have particularly strong views as a group on which one. I personally do have strong views on which one it should be, but that's a personal preference. The second thing is that more time for the DDF is expensive to slightly less for the wide field deep, or equivalently, do the DDFs when they're seeing is great. So having good seeing, especially to resolve more objects in the deeper fields, that would be our balance, that would be our trade-off. And especially U-band depth for the DDFs is critical. I wrote a white paper on the why, mostly because of the multi-wavelength data. All the multi-wavelength data is there, but U-band is hard to get, and so that's where LSST would be a phenomenal contribution. And this sort of circled back for us for the question is, when do we have complete information on a galaxy? And that's not just multi-wavelength, but also for the depth of the survey. So next slide, please. we were talking about metrics for the last workshop, for this whole workshop, and so I was trying to come up with a workable metric for when we have enough information on the main body of a galaxy. And the problem for galaxies is that they're fuzzy creatures, and so the longer you integrate, the more information you get. But the paper by Trillo argues quite nicely that a 1 solar mass per square kiloparsec is a good natural limit to any kind of galaxies. And so this would be a good way to apply a metric there, where you start, because the metric right now for extragalactic science is just we've detected the galaxy, not how much do we know about it. And so let's say you have a stellar mass that you put in your into your cadence simulation. You know what mass that galaxy is at what redshifts. You convert this to this R1 radius. You then convert that using mass to light ratio, the band shift from redshift to cosmological dimming from the distance, and the dust extinction from the Milky Way. And so you convert that to an observable in each filter. And so at some point, your cadence has hit the completeness, this R1. So we know all we need to know, or all we're really realistically going to get on this galaxy at a certain point. Now I have to say that for the Galaxy Working Group, we felt that we'll get there when we get there kind of attitude. Our science isn't going to be completely killed if we do a different cadence. But it is kind of, it will be very instructive to see at which point do we know enough, at which point is analysis going to surpass DES, for example, at which point do we learn more. Can I have the next slide, please? So this is the idea. We start with the mass distribution, we find out what the R1 is, and then we calculate what what the main body of the galaxy, when we have that main information. Now that I'm using these pictures, these images from Trillo's paper specifically to show that, yes, that is not all the information, like all the low surface brightness working groups, targets like streams, like feathering, all those things, those are below that level. But it should give us an idea which point we actually have enough information on a galaxy to say it's this. It's got rings, it's an elliptical, it's a disk, it's got this many spiral arms. That sort of information is probably when you hit that R1 radius, and depending on which filter, depends on what the cadences are. That should, the middle figure should show you, like, yeah, that R1 is actually good for anything from ellipticals to SC galaxies to ultra diffuse. So that is the idea.
No, lo devo cambiare.
Non c'è Ryanair, usi il biglietto di Andrea.
Okay,
So,
thanks. Was there an, oh, did you say
there was
you had
a,
one more slide?
there was a, I added a slide, but I'm not sure if I
Yeah,
was familiar with that.
I think I can reload it.
We are.
Okay, is that still being shared? Yeah, okay.
Yeah, so that's the to reiterate that all these kind of fields have a lot of multi-wavelength data already accrued on them. So the synergy relies on matching and having the exact position, like the AGN survey has said. And it's the final. It's a funny thing to realize that the LSSC won't be the final data on each of these fields. So it's not the last photon collected. This is just a plot that I recently made just to figure out how many redshift points we had in here and how many spectroscopic redshifts we had for, and also how well it was matched to the various radio surveys that were happening on there. So foremost with ESOS foremost will start operations, and all these fields, these deep drilling fields, have been prioritized there. So I think the synergy for the whole fields will be much more will be much richer than any particular cadence for at the moment for galaxies. We'll explore that more with some galaxy specific metrics like the one that I just described. But I think we are happy to wait for the photons to trickle in, and our cadence, the cadence itself, is not going to particularly kill any one galaxy topic. I'm happy to take questions at this point.
Okay, thanks. Yeah, so we are already over time. I'm sure Jelko is staring daggers at me, but I have my screen shut off for that. But anyway, yeah, any quick questions for Penny? Yeah, Meg, please.
I think it's partly related to what Lynn wrote in the chat. And the question I had when reading this cadence notes was, you want to rapidly get a deep drilling field with 10-year cadence. Isn't that what commissioning has to do anyway? It has to at least get to 10-year wide, fast, deep cadence in at least one field to test things out. And so I'm just wondering, is this something in operations can maybe comment? Is this something that will happen in commissioning or be checked into commissioning to be able to check that all the deep drilling processing works correctly? Or is Galaxy's able to use the wide, fast, deep 10-year test during commissioning as this data set to get started on these science objectives?
I can provide short answer. Yes, it's still in the commissioning plan. Originally, we were planning to go to 20-year depth, but then it was descoped to 10-year depth. And it turns out that 10-year of exposure time per field is about the same as 1 night of data. So you can do that in 1 night, and we still plan to do it.
Excellent. But I would argue to do it in all filters to make sure that we just to see if we actually perform as well as we can.
Yes, in all 6 filters. Yeah.
Excellent. Fantastic.
We are behind the schedule. So since DDFs have their own Slack channel, I would suggest to take other questions there and to move on.
Yes. So yeah. So the goal of this session was to try and get a consensus, and you heard certain ideas. And also, as Peter mentioned, they're going to do more DDF experiments shortly. So suggestions for what experiments to be done, I think, would be very valuable right now. And I suggest, yeah, as Jelko said, let's move that discussion to the Slack channel. So thank you, everyone, for participating in this.
Thank you. These were excellent inputs. Next is Angelica and 3 science collaborations that she is presenting. Representing. There we go. Angelica,
hello.
it's all yours.
Hello. Good evening. Launching the presentation. Just a moment, please. Counting. Okay. Dear friends, dear colleagues, on behalf of the session organizers, we thank SUC for providing us with time slot to present this session. Welcome to the trilateral session, Together We Stand. Our aim is to inspire and motivate further exploration of survey strategies that AGN TVS microlensing and strong lensing SC could attempt to optimize. Blazar studies and quasar accretion disk sizes measurements are 2 key intersections between these 3 collaborations. And here you can see some options for discussion topics. And it is an absolute pleasure to have our 4 special guests join us today who will deliver 5 high-level lightning talks. And in order to get through our agenda successfully, we will save time after all talks to address questions and discussions. And just as we should keep time slots, we will kindly suggest switching to another topic if a presenter exceeds 5 minutes. So I give the floor to the first speaker, Timo. You're welcome.
Hi, everyone. So I intend to be shorter than 5 minutes, hopefully. I think this is the second slide, isn't it? Do we have a slide before this one? Okay, so for those of you that were present yesterday, this is very much related to what we started discussing. So it actually ended up being a discussion about image quality on the first year. So I'm one of the Strong Lensing Science Collaboration chairs, and I'm here to advocate for good image quality, okay, like I did yesterday. And here I want to talk about a possible compromise of having better image quality during the first year only, okay? So here you can see a bunch of lenses. The scales of these objects go from a few fractions of an arc second to a minute or so, okay? Here on the left, you can see a histogram of the typical separation of lenses. And here you can actually see why good image quality is very important for us. And you can see how it drops pretty quick once image separation drops fairly quickly once we go to worse image quality. So if you can go to the next slide. This is a plot that I already showed yesterday. That is the median scene that we expect from, at least from the previous simulations. This is 1.7, I think. And we can see that the image quality is not very good, at least in the G band, that it's quite important for us. We explored a few different families of simulations, and we saw that these filtered dist and good seeing, some of them had a better image quality. Now, this came at the cost of co-added depth and probably number of visits in other filters like the infrared bands. However, what we propose is to have a different strategy on the first year. And then last slide, please. And this is the same simulation of the median scene, but only taking into account the first year. And what's most interesting for us, the median best epoch scene. So this would be the single visit depth image quality of the whole white fast deep area, okay? And you can see that it goes significantly better than baseline for, I mean, all of the different simulations that we tested, okay? So what we're suggesting is that if we would be very happy, for example, to follow one of these seeing optimized strategies on the first year, and then we can run the baseline strategy for the next 9 years. Now, it's important for us, maybe I don't have the time to explain, but it's important to us to find the lenses as soon as we possibly can, okay, to monitor for transients. That's it.
Thank you, Timo. You are very fast. We are going to the next talk, and we are glad to introduce Colin. Colin, you're welcome.
Thank you. Thank you for having me. So this is my pitch for having at least some Rubin light curves sampled with a cadence of a few hours. And so I'm interested in AGN variability. AGN variability is stochastic, but there's a characteristic time scale in the light curves themselves. So the plot on the upper left here is the characteristic time scale in days versus the Blackwell mass. So the characteristic time scale, sometimes also called the damping time scale. If you're familiar with the structure function, you can think of it as the frequency or the time scale where the structure function turns over in AGN light curves. So the black data points are AGNs measured from composite light curves from SDSS and DES, pan stars, etc. The quasars are the massive ones on the upper right. And as we go to lower and lower black hole masses, we get into Seyfert galaxies, and that data point right there is NGC 4395, which is a well-known dwarf AGN with a black hole mass of only 10 to the 4 solar masses. And so that particular source has a characteristic time scale of days. And when we extend this relation to stellar mass accreting systems, so those are the magenta plus symbols down there, those are nova-like white dwarfs, which have optical variability from a rapidly accreting accretion disk around the white dwarf. If we extrapolate our relation, we find it's close to what we would expect from AGN accretion disk variability. And so in between is timescales of tens of hours where we would expect an intermediate mass black hole that's rapidly accreting to show variability. And beyond that, the variability power would saturate and be difficult to detect. So AGN variability can be a probe of accretion physics for this reason. We think it can be a black hole mass indicator based on the timescale of the variability. and can be useful for identifying AGNs. So finally, just to summarize, on the bottom right is a plot of a simulated intermediate mass black hole light curve with a characteristic time scale of a few tens of hours. And we only need a couple nights of, these are idealized light curves, but we only need a couple nights of hourly cadence to constrain the time scale pretty well, even if the cadence after that is quite sparse. So that's quite reassuring, and hopefully this can be an interesting way to constrain the mass for potentially an accreting intermediate mass black hole or low mass supermassive black hole with active variability. And this, I would point you toward Eric Bellum's cadence note, which suggests that the hourly cadence is not well sampled currently. So this is my pitch to try to sample the hourly cadence a little bit better. Thanks.
Thank you, Colin. You have been very effective. So we are going to the next.
Angelica, you muted.
Okay, sorry. We are happy to invite Claudia to walk us on the border between the AGN and TVS cadences. Claudia, you're welcome.
Thank you, Angelica. I will present our results on the optimization of the Rubin LSST service strategy from the point of view of blazar variability. Blazars are active galactic nuclei, but they are also transient and variable sources, so our science case should enter the field of interest of both the AGN and TVS science collaborations. The cadence note, which is submitted in April, has been turned into a paper for the special issue of the FJ supplement. I received the message that it is accepted for publication just today. The paper contains a deeper analysis and more results than the cadence note, especially on deep drilling fields. In the sky map plotted here, each point corresponds to a confirmed blazar or blazar candidate according to 3 blazar catalogs. The BZ-CAT file catalog contains less than 4,000 confirmed blazars in the whole sky. The catalogs Kratos and Bros contain tens of thousands blazar candidates. So if we consider the 4 historic deep drilling fields plus the double Euclid deep field south, we have only 5 confirmed blazar deep drilling fields, but more than 100 candidates. Actually, we can estimate that deep drilling fields should include about 150 objects observable with Rubin LSST. Almost all of them should be detectable with a single exposure so that light curves will be available. Therefore, deep drilling fields should potentially be of interest also for blazar variability studies. And we investigated benefits and drawbacks of various OPSIM runs with the MAF. Next slide, please. So the conclusions of our analysis are the following. In the wide-fast deep, we favor visits with 2 snapshots of 15 seconds each to mitigate saturation of flaring and bright blazars. No cadence was found to perform much better than the 1.7 baseline cadence, whose main disadvantage is to pair visits in contiguous filters in the same night. In deep drilling fields, we expect only a few bright sources so that the problem of saturation should have a limited impact, and cadences with single 30 seconds exposure, which provide much more sampling, may be adopted. However, with respect to the baseline, a more beneficial cadence should include shorter exposure sequences more often, and in particular, intranight observations of the same deep drilling field with more time spacing between visits in the same filter. A deep drilling field observing strategy like that included in the daily DDF OPSIM run represents a better choice than the baseline implementation. But this can be further improved, introducing a more homogeneous sampling of the different variability timescales, as also proposed by Eric Belm in his cadence note. In both wide, fast deep and deep drilling fields, visits with different filters in the same night are required to obtain color indices with data close in time, which is necessary to avoid bias in colors due to variability. This means that the same field opting rounds are detrimental. Color variability and trends with brightness are stronger when colors are obtained with data in filters that are more separated in wavelength. Therefore, in both wide-fast deep and deep drilling fields, the choice of filters to pair in the same night should prefer bands that are not contiguous. We favor an extension of the wide-fast deep footprint to the north with an enlargement of the low extinction extragalactic sky, which would also be reachable by many more observing facilities that could complement the Rubin LSST monitoring. But this should be accomplished without decreasing the sampling. Observations at higher masses can be beneficial, as they can prolong the observing season and lead to smaller gaps in the light curves. And finally, as blazars are believed to be neutrino sources, it would be great to consider target of opportunity observations when neutrino facilities detect high energy neutrinos of astrophysical origin. Thank you.
Thank you, Claudia. You are perfect. Timo, you're welcome to present once again, but something about accretion disks.
Yes, hi everyone, it's me again. But as Angelica says, this is a slightly different topic. So this is something that Desk is interested in this, and the AGN community hopefully is interested in this. And this is about lens quasar time delays and microlensing. So this is the transient nature of lens quasars. So we have variability in lens quasars that can be due to two different things. One is intrinsic variability plus time delays between different lens images. And you also have microlensing. Okay, microlensing is uncorrelated variability between the different lens quasar images due to stars within the lensing galaxy. Okay, that produce sort of like a lensing on top of lensing. Okay. These are used respectively. The measurement of the time delays can be is directly related to the size of the universe and more specifically to the Hubble constant. No. There you go. And then microlensing can be used to measure the structure of accretion disk. I naturally do not have the time to go into details about this, but different geometries of the accretion disk would show different magnification light curves due to microlensing. Okay. On the right, you can see a lens quasar. You have the 4 images of the lens quasar. No. Can you go back? Okay. So on the right, you see a lens quasar where you have the 4 images that are varying. And here you have the two phenomena. First, we can measure the time delay by comparing the different images. Once we have this time delay, we can shift the light curve, subtract them, and then we obtain the pure microlensing light curve. So this variation that you see in B-A, C-A, D-A is due to microlensing. We compare these two simulations and we can obtain constraints on the geometry of the accretion disk. Now, before moving to the next slide, the timescales involved here are, for the time delays and intrinsic variability, are quite different. So can you still go to the first slide? So the quasars vary at the timescales that you know. I mean, this can be from it's anything. I mean, from minutes to years, and then the time delays can also be from minutes to years. Okay. So what we do to measure time delays is identify these very identifiable flares or intrinsic variations that we see again a couple of days, a couple of years, a couple of months later on another image. In microlensing, the timescales, however, are of the order of years to decades, but they are very rare. Okay, so we don't expect that many microlensing events, and we don't expect that many quasars in the sky, that many lens quasars. So LSST is the ideal survey for these two science topics. It's a very wide survey that is basically looking at the sky, not at very high cadence, but at a cadence that is good enough. Okay. Now we can move to the next slide, please. So one thing that we've tested with these two science cases is rolling cadence. As soon as the idea of rolling cadence came upon the survey a couple of years ago, we were a bit concerned because rolling would naturally imply that the seasons are sort of like shorter. So you have larger holes. Since we don't know when the variation is going to happen for either of these two science cases, we wanted to see whether a rolling cadence would affect us. And it seems to be the case, okay? So on the left, you can see our estimate of the number of golden time delay lens quasars. So these are very good quasars where we can measure time delays very accurately. And relative to baseline, the percentage of systems that we find, okay? So uniform cadence are in general much better than rolling cadence. Now, we know that this metric might have an issue, but still the qualitative case is there. If we don't see the event, we cannot measure the time delay. And the same is true for microlensing. So this is another test that we did. These are the old simulations. These are the minion simulations. I don't know if you remember this. And you can also see the same thing. What we're seeing here is the fraction of events that LSST is going to be able to see in one particular lens quasar, the same one that I'm showing you there, that it's a sort of like a typical lens quasar, and it's separated by band. So you can see that larger bands that come from a larger accretion disk size are generally longer in timescales, so are easier to find, okay? If we go to bluer bands, we're looking at a smaller region of the accretion disk, so the events are shorter and harder to find. And that's what you can see in this weird color plot. But the main idea to take from this plot is that, again, a rolling cadence is going to lose more events than a uniform cadence. So I am a bit, not too much, but I'm a bit worried that the new baseline will have rolling, and we still need to test these two things with the new baseline. That's it.
Thank you, Timo. You're perfectly on time. I'm sorry for switching these slides. And we are coming to the next presenter, Jeff Yu, from Dark Energy Survey collaboration, and he will present about, once again, about accretion disk sizes, but measured from the data in star and supernova fields of this survey. So Jeff, you are welcome.
Okay, hi everyone. I'm Zhefu Yu, a graduate student in the Ohio State University. And here I'm going to talk about the measurements of the agent accretion disk sizes using the data from the DS standard star and supernova fields. So the supermassive black holes grow through accretions in agent phases, and understanding the accretion disk is important for understanding the growth of the supermassive black holes. Specifically, the size of the agent accretion disk is a critical parameter for constraining the accretion models. And one of the major techniques to measure the disk size is the continuous reverberation mapping technique, where we measure the time delay between the variation of different photometric bands. And this time delay corresponds to the light travel time within the disk, and therefore indicates the disk size. And in order to measure this continuum lag, we need to monitor the target for many years with relatively high cadence. Therefore, only the large sky surface like DES and the upcoming LSST can possibly provide a large sample of the disk size measurements. And in my 2020 paper, we used the first 5 years of data from some DES fields to measure the disk sizes. And the left figure here shows the distribution of the observational cadence on those fields. So the DS standard star fields have about daily cadence, while the supernova fields have about weekly cadence. And in this paper, we measure the disk sizes of 22 quasars. And in the right figure, we plot them in the disk size versus black hole mass plots. And the 3 dashed lines in the figure shows the prediction of a standard thin disk model with different Eddington ratios. And our measurements in this paper shows general agreement with the prediction of the standard thin disk model. However, there were previous studies where they found significantly larger disk sizes than the model prediction in some local AGNs. And in order to address this discrepancy and further understand the physics of the accretion disk, we do require more measurements of the disk sizes. So next slide, please. So here the LSST deep drilling field can lead to a significant improvement in this field of study. So the deep drilling fields also overlaps with the DS supernova fields, which we already have many years of photometric monitoring from DS and also spectroscopic monitoring from the OSTED survey. And the upcoming LSST observations would significantly increase the data quality on those fields. And we expect that the number of disk size measurements from LSST era would be an order of magnitude larger than the number of existing measurements of the disk size. And those new measurements would also have higher quality due to the deeper LSST observations. And one lesson we learned from our experience in DS is that the observational cadence is quite critical to the disk size measurements. And we performed some simulations for the LSST deep drilling fields to further test this effect. So the left figure here shows examples of the simulated light curves we create with different cadence within one observational season. And the upper panel in the right figure, we show the fraction of the continuum length that we can successfully measure from the simulations as a function of the input time lag, while the lower panel shows the distribution of the predicted time lag for the Sloan quasars. So here it shows that there would be many quasars that have relatively small continuum lags. And for those sources, if we change the observation cadence in the DDF from 3 days to 2 days or 1 day, then we can significantly improve the yield of disk size measurements on those fields as shown in the upper panel. And this result also agrees with the requirements for some high cadence in the agent cadence nodes discussed by Neil in the previous session. Okay, that's it for my results. Okay, thank you.
Thank you, Jeffo. Perfect.
Hi, Angelica, can I help you now with the discussion?
Yes, of course.
So we kind of have a few minutes left for some discussion, and we put a slide with basically a goal of this session, which was to identify the overlapping items between the three subgroups and this, within the science collaboration. And so we just want to take up either some of the topics that we put here or any suggestions from the community related to the topics presented. And there was some comments in the chat. I can read that up related to the TIMO's plot. If you want to comment this, Timo, or I can read it up.
That's fine. I don't know if you saw it, Jelko. If this answers your question, it's
yes, it does.
It's a 10%. It's a 10% loss basically on golden lenses for rolling cadence. But again, we need to take this with a grain of salt. This is something that we're tweaking with Lean. We expect it to be worse. Okay, it might not be 10%. It might be slightly more than 10%.
Yeah, you scared me. I didn't look at the axis. I just saw the two blue histograms and it looks like rolling cadence kills it so badly. How can that be?
No, 10% for now.
That's okay.
Okay, do we have more comments or suggestions from the audience?
I had a question for Jeffou, if that's possible.
Yes, go. Please.
Okay, so Jefu, thank you for those nice simulations, which are very helpful in supporting this requirement of the AGN science collaboration. In your simulations, just a couple of questions. What minimum length of this very dense 1 to 2 day sampling do you think is necessary to get good lag recovery? And then in your simulations, could you also comment briefly on how you modeled weather losses and how sensitive recoveries are to weather losses?
Starting from your second question, so about the weather losses. So at that time, I just briefly running through the OP thing and do not take very detailed investigation on the weather loss. So I'm not sure how to answer that question. And about your first question, so are you asking, what's the minimum cadence we require to get good recovery?
No, I meant how long of a period of this 1 to 2 day cadence do you require? In our simulations, we thought you would need a couple of months of that density, but what are your simulations indicating?
Yeah, so in this simulation, we are using generally a uniform cadence for the whole observational season. So it's several months.
Okay. So very long. So,
yeah.
so 6 months or more. Okay. I mean,
yeah, but
it would be valuable to know if you know, our simulation suggested that you might be able to shorten that down to save time, that down to say 3 months or even 2.5 months, and still get a good lag recovery. But I'd be interested to know what you find whenever you're able to simulate that. Yeah.
Yes, so this is kind of early work. So at that time, the cadence node on the accordion cadence is not out. So we just simulated a uniform cadence. But I suspect that if you make the length shorter, then it would also be likely some good recovery, but it is not simulated in this early work.
Okay, thanks.
Thank you, Neil. Any other comments, suggestions from the SOC maybe?
I will thank you for preparing all these slides and getting people to contribute. I propose we continue. The next one is Will Clarkson with missing metrics for galactic science.
Thank you, Željko. Thank you, everybody. I'm just going to paste in the links to the slides for what you're about to see, and then the live notes here. So they'll go into the chat. If you'll bear with me just 1 second, I'll get my screen sharing going here. Okay, so let's see. Okay, if I do that, can everybody see my, there should be a slide saying missing metrics. Can everyone see that?
Everything okay, Neil?
You do.
Okay, cool. Thank you very much. What have I got, Željko? 20 minutes?
Altogether 30.
Okay. Yeah, so thanks very much, everyone. So this session was proposed to help get the various science collaborations over the finishing line to get metrics contributed to the SCOC on the timescale for which they need it. So just a couple bits of admin. There is a Slack channel for this session, and questions posted there will be persistent. So we can read them after the meeting. There's also a live notes Google Doc for this session, which I believe Rachel Street has kindly taken notes for. Like I say, while SMWV and TVS and DESC proposed this session, this I think is relevant to all of the science areas. So I hope it's useful to people. So the plan for this session is roughly this. I'll say a few words of introduction and motivation. Most of the session has been planned to be discussion in this session from people in the room around two broad topics, one of which is existing metrics that now need changing into math, which I'll explain in a minute. The other one is science areas that we know are important that do not have metrics at all yet, and then there'll be a wrap up if there's time. So just to set the scene a little bit here, I think everyone here has read this phase 1 draft requirement, but we were told quite categorically earlier in this workshop that observing metrics of the kind we've heard about in the previous couple of sessions here, observing metrics that are not incorporated into math by the end of 2021 risk not being included in the SCOC's phase 2 deliberation. And so this session kind of takes that seriously, and we sort of run with it. The reason that's particularly interesting to galactic science is because I think it's still true that's an area in which we know there are metrics in development, but there's big gaps in the metrics that have been actually incorporated into maths. So that's sort of why there is a focus in the proposal. But every input is welcome. I think every science collaboration is in the same boat in terms of needing to finish up metrics. And so based on a quick look at the metrics in process and then the science areas people are providing feedback on, at least to the SMWV and TVS co-chairs, these missing metrics seem to divide into two broad categories. One would be metrics already coded in some form, normally a Jupyter notebook that needs translating or simplifying into a form that can be run within math. One good example of a completed metric would be the brown dwarf metric by John Giesis and Peter Yoakum that we heard about, I think, yesterday. And the idea is to populate this with metrics that will help us to understand how well these strategies work for our science, as you've heard many times, I think, in this meeting. And to that end, I'll show in a minute, there's a huge amount of work being done for these metrics among the communities that are still being developed into a form that can be turned into math. And several people who are working on these have very kindly contributed slides, which you can find at the end of this slide deck. I don't think we'll have time in the session for those to be presented, but I do encourage everybody working on metrics that are relevant to galactic structure, at least, to take a look at those. And then the second category is science areas that we know are important, but for which there are no metrics yet. There are several important areas, including, for example, star clusters in the interstellar medium, for which there does not appear to be a metric under development as far as we know. And therefore, this is also partly a pitch to sort of try to help people in that category to get things ready on a time scale that's useful to the SCOC. So most of this session has been planned to be discussion of those two issues, and the idea is to sort of help the community tell the SIMS team what they need, and also for the SIMS team to make sure that we know what would be helpful to them. So Lynn, Peter, and Eric, what would be helpful to you to help us help you get the metrics across the finishing line for December. So so to try to tame the madness, I think this has been shown in a previous session. TVS actually led the development of this. There's a spreadsheet coming out of the hackathon from last year, from 2020, in which the metrics that the community were working on have been gathered. And as I think Rachel explained yesterday in one of the main sessions, these are the idea is to gather these into science areas, into these so-called metric packages. And so I'll switch across to the spreadsheet just to show what this actually is. And one of the goals of this session is so that by the end of this week, the tab in that spreadsheet that's organized by science area will have useful, up-to-date information that the SIMS team can use to help the community, and that the community can use to help the SIMS team. So we can sort of meet in the middle and get that done. So the link is in the slides here. It's also in the chat and in the SCOC2 Slack channel. And so we've added a couple of details to that spreadsheet to make it easier for participants to turn that into a list that can be used and understood. So I'll show that quickly, just to try to help set the scene here. So you should all be seeing now the spreadsheet tab. There should be a fairly bewildering spreadsheet. Is that correct, or do you see something else?
We see your spreadsheet.
Thank you very much. Yeah, so there's a main tab here that I won't spend much time on, except to point out that it shows this enormous amount of effort that the community has been doing to produce these metrics, along with indications of status for the individual metrics for this. Given that we're working to a December timescale to get these metrics done, that's a little bit overwhelming. So actually, I think a better tab to use, the one I recommend, is this metric packages tab. That basically gathers together by science case the metrics or combinations of metrics that people have identified to develop their science for comparing against OpSIMs. And so depending on which category people fall into, whether you have a metric that you're already working on that you will need help to convert into math, or whether you have a new idea that needs a new metric, that's what the green and the yellow areas in the spreadsheet are for. If you have a metric or metric package that you've already been working on, those are the green areas in this spreadsheet. And I would request that people who are working on metrics, please make sure that you update the status by the end of this week, ideally with today's date, so people know that you've updated it. And if you can, some indication as to how complete you think your work is. If you think you're near the finishing line, please indicate that. There's also a new column, also in green, for people that are working on existing metrics. If you have a link to your notebook or your code, it would be very helpful, I think, to the Sims team if you could provide that in this column here as well. So in terms of what people do after the session who are working on metrics, if you have an existing metric you're working on, I recommend checking and populating the green areas in this metric science packages tab. For people in the other category, if you have a science idea that you've not seen discussed in a metric, that's what the yellow regions are for. So there's space at the bottom of the spreadsheet here for people to enter in new metrics or metric packages that you want to do. And again, I think practically, given that we're all under a deadline of December, the simpler that is, the better. And I think in terms of whether it can be developed from existing metrics or not, if it's in terms of existing metrics, that's also better. So I've mocked up here an example for galactic structure in the interstellar medium, just using the subgroup lead's name to lead that, and where I've sort of sketched out what the ultimate calculation might be, what quantities are needed, and then if people know this, what metrics to use, and then some notes if those are helpful. And the intention of all of this is to be able to gather information to help the community add information in a way that would be useful to the Sims people, to work with the community to help get the metrics in place by the phase 1 requirement from the SCOC. So that's a lot of information, but basically the aim for this session is to help people actually do that, to be ready for this. So I've put notes in the slides here for how that might be done. So this is a recommendation to fellow community members who have metrics either that they're working on or that there are science areas that they know they need to have metrics. A request to please, after the session perhaps, please fill these in. So if you already work on a metric, it's helpful to update the spreadsheet with the status and a link to the code. If there's a new idea that you have that doesn't exist yet in a metric, as far as you know, it would be useful to specify that such that when you do talk to the Sims team, you have something useful to tell them that they can work with. So that's what I had to sort of try to set the scene and try to help people have some context for discussions and efforts to come next. In terms of the discussion, I've written a few prompts into the slides here, and I'm not entirely sure how the session is going to go. So if people have comments or questions, I'd recommend just raising a hand in Zoom or typing it into the Zoom chat. Or if you want your question to be persistent, I recommend adding it to Slack in the Missing Metrics channel. So I thought we could divide the time we have into two sessions. One would be one after the other. One would be people who are working on metrics already, and the second would be people who have ideas for metrics but aren't maybe sure how to get started. So for the next up to 10 minutes, I guess, I'd like to open the floor for discussion about people working on metrics that they know that they're working on, but it may not be in math yet. Some of the prompts I have here that may help people sort of start to discuss. If you're working on metrics that are not already included in math, have you contacted the Sims team yet? And I guess I've just covered this in the opening remarks. If your metric is already listed, what is the current status? And can you please update the spreadsheet with that? I think a bigger question that this may be the roadblock that many people in this community are finding is, if you do have a metric that or a measurement that you're trying to convert into math, what has been the biggest roadblock? And can you identify at this stage, what help you need in doing this? And I have a question for the Sims teams, a discussion prompt for the Sims team as well, based on some discussion that happened in the previous session this afternoon, which is, what input do you need from the community in order to make it easier to get metrics into math? So I'll stop talking and I'll open the floor to questions or comments anybody has about metrics people are working on that need conversion into math. I see Meg's hand is up. Meg?
Yeah, I might add a point to your question. Your prompts is also, do you need your metric? There is it's nice to have this because it can measure X, but if you have something that's a proxy, right, that does good enough, is that enough? For example, in solar system, there's we're not running a comets population. We might want to, but there's a lot of other things we can use, like number of visits, how it impacts outer solar system, to give us a good enough idea that hasn't been such a strong driver to make one like a metric that includes the comets. We might think about it, but we might not. And so I think it might be something else of, is there something that's already there that's close enough as well that could give you the proxy for your answer, for your testing whether your science case is being impacted?
Yeah, I think that's a really important point, particularly given the timescale. Yes, if it turns out that existing metrics already answer the question, or if they're proportional to the return that you expect to get for your science, and I would agree that that's useful to know. But I think I still recommend adding that to this community spreadsheet, just so that you know that science, others know that science is actually being considered. Would be my reaction to that, but perhaps people in the room have additional comments on Meg's point. Okay, let me go over to this. Oh, do I hear a question?
I had a question about the metrics packages, because I was poking around in some of them. How up to date do you think the comments about like integrated with math or not are? Because one of the problems that we've had in the Sims team is when somebody comes to us and says, oh, I have a metric for X. And from our point of view, we already have a metric for that. But it's because their metrics are, well, no, ours is actually a little bit different because, you know, and here's why. But especially if we're just looking at the sheets, then we don't know. So one of the examples I had when I was looking at this was the transients one, the transients metric packages page. So for example, there's number of kilonova detected and the dev status says ready for math integration. But as far as I know, we have that and we're running it on all of the simulations.
That sounds like a case that could be quite straightforward for the community to deal with then, because if you are on the transients group on this call and you're hearing this, I would recommend that you update the status in the spreadsheet to say is already being run. Is that what you're asking there? If the
I would, because I know you guys have been working really hard to get this all together, and there's some of them in there that I'm like, we actually do have this already.
So I think a suggestion that would then be for the community would be to please make sure that you do update this column and status, so that this prevents any additional effort for chasing down something that's already been done. Yeah, so as far as but to actually answer your question then, as far as I know, that status column has not been updated in some time. Oh, I see Igor has his hand up with a comment. Igor, would you like to comment?
Yes, please, just commenting on the last statement. Just to clarify that some of these packages, as we call them, sometimes are just basically a collection of information that should be the information to be looked at the most, and doesn't necessarily mean that there is more work to do. Actually, the hope is that most components of these packages will be already fully implemented. So I think this is useful feedback, and we will make sure to indicate what's already there and what's missing. So thank you for that.
Lynn, does that address your question?
Yeah, that would be, I think so.
Okay. Okay, we've got a few minutes left for any additional questions or comments. Rachel.
Just to jump in, would it be a good idea if when people update the spreadsheet, they update it with a date to say this was updated on, so that we know for any updates that may have expired?
Yes, that's a good point. I'm going to embolden that. Yeah, I think that's a good idea. Lynn, would that be helpful to you and the simulations team?
It's not obvious. I mean, certainly if they update it and the date is very, very frequent, and we have something we know we've had for a while, that is helpful. So yeah, it's helpful information, as long as it is actually updated.
Okay, thanks. Okay, I see Poshak has his hand up. Poshak, would you like to ask a question?
It's more a comment. So Will invited me over here to contribute a bit, just to say a bit about what we're doing. We are interested in characterizing orbital periods in accreting systems and X-ray binaries. And one of the comments, I think it was Lynn or Meg just made, I'm sorry, I'm not sure who said that, about proxies. I believe there are many metrics dealing with binary period characterization. When we talk about X-ray binaries in particular, there are a few characteristics that are unique to them, including quiescent level flickering, the fact that they have certain spatial distribution and also magnitude distribution, etc., which are particular to them. So I guess my question is, I guess it's not always obvious to know whether a proxy metric suffices or not. And so how would one determine that? If we wanted to try and understand that a bit better, would it still be okay to get in touch with you? Would that be the right thing to do? And just to say, I prematurely, we did do some work on this, but I prematurely posted a link on the chat. Just going to post it again, just so that you can see what I'm talking about. We actually looked into this back in 2019 with Will as well. And the link is posted there, but this all needs to be updated with the latest cadences, etc.
I think I would say from my point of view as someone on the SCOC, it depends how important that is for your science case. If you're like, well, it was a 1% hit versus a 5% hit, we don't really care, right? Then maybe that the proxies are helpful. Because I think on the same side is your niche science going to drive the cadence. So there's lots of metrics for lots of things, but if they're all little pieces, transient science, we're going to have to decide everything's going to vary differently. And so I think that's something to think about as well. So is it worth that time and effort if you're like, this is a 3% effect, but we want to make sure it's not a 20% effect, then the 20% effect, obviously the proxies are going to show you that. And I think that's the thing to think about. Lynn and Peter should definitely comment as well, but I think for me, that's the way I've been thinking about these metrics, is that they're guiding us to make sure we don't make really bad decisions. But if you're looking at a 2% effect, at that point you're like, what is that incremental science or not? And if somebody else takes a 20% hit, should we be changing things to make sure that science area doesn't take a 20% hit for something that would take 1%? So maybe that's my perspective of, if you're like, this is absolutely crucial for my science, then maybe that's something you need to explore and get an exact metric. But if you're like, I just want to make sure things are going okay, and it's not going to tank my science completely, then maybe the proxies are good enough.
Okay, thank you. Yeah, I'll definitely think about that and might get back to you. And I see Eric has a comment as well. Yeah. Okay, we should move on.
Okay, thank you. Great. Okay, so any more questions about metrics in progress before we move on to new science that needs completely new metrics?
Will, I think we should speed up a bit. We have 27 minutes to the end, and
so
people may have other meetings after this one, and we still go through TO.
Okay, in that case, let's actually, we can probably finish this fairly soon, actually. I think in that case, rather than have discussion on the new science that requires new metrics, I'll just flash up the discussion prompts for people to think about. And then I think the best way to wrap this up then, so we can move on to the TRO session, I'll actually just flash up again the recommendation for how people can communicate the status of their work. So I recommend that people, if you have an existing metric that you're working on, I recommend that you update the green areas in the spreadsheet, and please, if you can, date them, at least for the moment, so that people know it's been updated recently. People with new science ideas that have not got a metric yet, but which you think it would be straightforward to do so, I recommend filling in the examples down here on the spreadsheet. And the idea is that this then forms one place where we know that there's a running record of what people are working on and what to expect. I'd also suggest a piece of advice that Lynn actually recommended in the previous session right before this one, which is that if you're working on something and you're not sure how to put it into math, talk to somebody else. It can be the Sims team or it can be another group working on metrics. Either way, the process of this pair coding can be very helpful. So with that, to give the TRO folks time, I think I'll finish up there. The link I recommend people look at is the link to the metrics tab at this Google sheet. I remind everyone that there's also a live notes document in the chat you can see, and then I think I blew past it, but there's also a community post by Lynn and the Sims team about more information on how to do this. So I hope that discussion was useful. as I said at the beginning, there's a Slack channel for missing metrics, which will help us, I hope, talk to each other and talk to the simulations team. But unless anybody has any burning questions, I think we can move on at this point. Okay, so folks who want to follow up, I recommend looking at the Slack channel for this. And thank you all very much for your attention.
Will, thank you very much for preparing the slides. We are going to move on to target of opportunity discussion led by Igor Andreoni. Igor, it's yours.
Hi, thank you very much, Zeljko and everyone for letting this session happen. Today we have several speakers, and the first one we will have the honor of hosting the Director of Operations for Rubin, Bob Bloom, who will tell us about initial ideas about policies for TOOs. And I think Rafaela is going to drive this slideshow. Raf, is it you who are sharing at the moment?
Yes, it's me.
Great. Thank you. Let's move then to the next slide and leave the floor to Bob.
Thanks. Thanks, Raf, for driving, and thanks everyone for inviting me to chat with you today. I wish I had more time to spend with the overall meeting. It sounds quite interesting. So let's just talk a little bit about TOOs and where we're at, and get on to the science, which I think will probably inform some of the questions that or open items that I raised here in these few brief introductory slides. We do expect, of course, that there will be TOO observations with Rubin at some point in the survey, and perhaps regularly throughout the survey. We'll see how things go and what the need is. There is no, as of yet, no written policy, but we certainly have been discussing items that need to be clarified, and probably sooner rather than later. I will say just parenthetically that we're in the midst of a giant review for the first phase of full survey operations, and when that's done early next year in February, we'll turn our efforts toward ironing out some of these policy issues, and this will probably be one of them that's high on the list. So we don't yet have any policy about what we would do, what we do with the data after it comes out, etc. What qualifies as a TOO. But let's talk about a few things that might help clarify or lead to discussion. So Raf, next slide, please. So the only detailed case that we've had any real discussion about, at least that I have with the team and others in the community, is of course gravitational wave follow-up, the sources follow-up. There is a document, a technical note that you can look at that Eric worked on with some of this. It's really more about the strategy for reducing data and getting it in the hands of people if we did get a TOO for a gravitational wave source. It's not so much about policy, but it's useful to start thinking about. In the pre-pandemic era, of course, we were looking toward LIGO 04, and it looked like the schedule with Rubin would line up pretty well with that. I say here it looks like a clean miss, but Eric tells me that it's been 04 has been revised outward a little bit to December. That still probably puts it in a very difficult spot, because if you work the little numbers there, that would mean right in the middle of the end of science verification, we might be up and running with the full system, and we might consider something like a TOO, but it could be a difficult time. So it's probably more useful to think about 05, and when Rubin would be fully operational. There are other wavelengths and facilities that we should also be thinking about, of course, to coordinate with TOOs, perhaps radio facilities or other things that are going to provide alerts and real-time objects of interest that we might consider the need for Rubin to follow up on. One of them that you may have heard about is an ultraviolet satellite from an Israeli group called Ultrasat. They've actually proposed, as part of an in-kind contribution, to share some small number of TOOs every year, where either collaboration could decide to coordinate with the other if something of great value came up. So I just throw that out as a particle for your information. Okay, next slide. So, where are we? What are the types of things we thought? I mean, certainly the bar should be pretty high for using Rubin as a TOO machine. It obviously has a very programmed observational way of operating. So, and it's a very specific and highly capable machine for covering the sky. And you'd have to ask, certainly, for any given TOO, do you need Rubin, or can you do it with some other facility which would be capable of doing it, even if it might take a little bit longer? I think thinking of a few % max time per year that might go to TOOs, which I think fits with what is in the SCOC and the Cadence simulations group thinking right now. So I think that's probably okay. It should probably be more than that. I think the proposals for TOOs should be peer reviewed. This hasn't been widely discussed yet, but I think that would be the way to go. This would be the same for any other telescope that Noir Lab operates, for example. Just director's discretionary time wouldn't be ruled out, but you'd have to ask, why would there be something so special that no one thought of it to get community buy-in in advance, as we do now with TOOs all the time on our telescopes. And it would be straightforward, of course, to run proposals through the Noir Lab TAC process, for example. Data taken on any TOO, I think, would be provided to anyone in the Rubin community at the same time. And so proposers would get to kind of define the experiment in this scheme through the proposal process, but everyone would get the data. I don't see any strong case for saying that someone should get a proprietary, very proprietary access to Rubin Observatory. And then I write here that it's not clear to me, at least, whether or not the data would be world public. I mean, if you think about TOOs and you think about gravitational wave follow-up, for example, it's like an alert. We would probably handle it or try to handle it much like an alert. And so maybe the best thing would be, it would just be handled like any other data product from Rubin. But I don't think we've thought enough about what the full scope of TOOs could be and what data the community might need to really understand it. And if it came from Rubin, if we thought for any reason that there might be more data needed, like image data particularly, that would cause an issue with our data rights policy, and we'd have to think it through. So those are my initial thoughts. I'm happy to take discussion. I don't know how Raf wants to, or Igor wants to run this session. We could obviously just wait till the end and wrap everything together, or we could discuss now.
Yes, thank you very much, Bob. I think the idea is that we all present some content and then we leave the discussion for the final minutes, so that if people want to drop out, they're free to do so, but we can continue a few minutes past the hour if necessary. So thank you again. And Ralph, would you like to tell us something about why target of opportunity observations will be needed with Rubin?
Thank you, Igor. Yes, just a few minutes. It's just a quick advertisement about the beautiful science that can be done. So if you tune out for the next 5 minutes, just remember this thing, that with less than 2% of time of Rubin, we can actually do revolutionary science that could be missed otherwise. And that's the whole message that I want to convey. So I just want to remind ourselves, so what are the key things that we can do right now in this world where we can follow up stuff in the gravitational world and with photons. So we have this opportunity basically to map for the first time both the pre-merger conditions and the post-merger conditions by putting together these two carriers of information. And just a few highlights of physics that we can do. We can study basically the properties of the ejecta, all the types of ejecta from these neutron star mergers, which is the way that we have to actually pin down fundamental physics. So I'm just going through very quickly through a few highlights. So what are the things that we could be doing with Rubin observations? So we are talking about the kilonova signature here. So we would be able to constrain how much mass and how fast that mass was ejected. We could also start thinking about the chemical composition of these ejecta. once we do know where to repoint, thanks to Rubin, we would be in the position to take spectra and understand how many elements have been formed right there. This is one way that we do have, one very clear way to actually study the chemical enrichment of the universe through neutron star mergers. And here I'm just emphasizing this beautiful spectrum, infrared spectrum of 170817. So this is just one side of the game. With these very same observations, we could also learn about fundamental physics. And here, what I'm thinking about is learning about the end state of this end product of these mergers, which is a way to constrain the equation of state of dense matter, but also cosmology. If we don't care about dense matter, some of you might care about cosmology. That's also another way, independent way to maybe solve that puzzle. All of this relies on one thing, which is to find that EM counterpart. And this is where Rubin clearly comes into the picture. So after 170817, where is the frontier in this field? Where the first thing is that we have n equal 1 object. We want to have populations to study the diversity of the outcomes of these mergers. So the other thing, even within 170817, we do not entirely understand what happened there. And specifically the blue component of the kilonova is one of the huge mysteries. So we are very interested in understanding what is the physics driving that and what might be other new emission components that might be there. And here I'm just emphasizing the free neutron precursor that might be one of the things that we might be able to capture if we get on target very, very quickly. Of course, the next breakthrough in my mind is the discovery of the NEM counterpart of a black hole neutron star merger. And we know that this is a very tough game. It can be an all or nothing game, but still it's completely open. It's completely open as a discovery frontiers. And then the question is, are black hole mergers producing anything at all that we can detect with photons? And final point, we also know of, we do expect to find unidentified gravitational sources. Can we say something about their counterparts? Can we say something about what these are? So to summarize, to do this science, which is, in my personal opinion, completely revolutionary, we need two ingredients. We need to go deep, and we need to be able to cover the entire or most of the GW localization region in the sky. And we need to do that promptly. So we need to put together these two key ingredients in the recipe, deep and promptly. And that is where Rubin can play a unique role. And it is where luck, with luck I mean just relying on covering that area of the sky just because the survey is just happening to go there is not a good idea. And it's also not a good idea to do galaxy targeted searches just because here in the era of SST, we're talking about bigger volumes, and we don't even know where the galaxies are at larger distances where the GW sources will be found. So putting everything together, we need to go deep, we need to do it fast. This is a complex plot, a little bit busy, but I want to drive home one point, which is that the counterparts tend to be faint at the typical distances where GW sources will be found in the next observing runs. And if you put there the typical limits of other surveys, and here I'm emphasizing DECAM and ZTF, you can see that really the only way to play this game is to actually use a much bigger glass like LSST Rubin. So we started pushing on this in 2016. We produced our white paper in 2018, which was approved to implement in the 10 years LSST simulation. And where we sold, our main point was that LSST should be a discovery machine, and Rubin should be a discovery machine, not a follow-up machine. And the update of that happened thanks to great work by Igor. This is our paper that was submitted to the FJ supplement. And I put there the link. So again, I close with the message that I started from. It's a few percent of time, 2% or less, but this is a type of science that is completely new and can't be done otherwise. So I think we have a tremendous opportunity here if we play the game in the good way. And that's all. Igor, no, I think, then we go to, Igor, it's you.
Great, thanks, Rafaela. That was a very rich presentation in very little time. So appreciate that. I would like now just to say a few words that complement Rafaela's presentation, basically trying to say how can we achieve these objectives. Next slide. In practice, if we want Rubin to be a discovery machine, how can we make that happen? In my view, in our view, the main step probably is the detection of the counterparts. Very simply, we want some photons from the counterpart to be detected by Rubin and so that they can be used to do any type of science. To be able to enable detection, there are several steps that we want to go through. First of all, we may want to select smartly which gravitational wave triggers to follow up, especially if during 05, 06, so in the future, it will be routine to find binary neutron star and neutron star black hole mergers, especially at very large distances. Timing is another very important factor, as Rafael explained. And also we want these observations to happen rapidly, yes, but also at several time scales, in the order of a few hours up to 1 or 2 days, so that we can really cover the whole phase space of light curve that we could expect coming from kilonovae in this case. So the optical and infrared counterpart from this type of mergers. In addition, as I want to stress again that deep exposures, especially on nights after the first, might be needed, in particular for neutron star black hole mergers or the most distant events. However, this might not be enough to just have some data that include the counterpart, because Rubin is powerful, and in the volume that we will be able to probe, thanks to this target of opportunity observations, we risk to have tens, if not hundreds of transients that we will have poor history, we'll know little about their evolution, and up to tens of supernovae every night could explode in that volume. So first of all, we want to maximize early discovery of a counterpart, early identification of a handful of possible candidates, because that will truly enable the multi-wavelength follow-up that will lead to the great science that we want to do to make this revolutionary science happen. And very much importantly, we have to be able to distinguish a few kilonova candidate or counterpart candidate in general from the very big number of contaminant sources. Next slide, please. So in practice, how can we make this happen? In the paper that Raf mentioned before, we're suggesting to perform at least 2 observations in multiple bands on the first night that is available for observations after a merger happens. It's very important that we have at least about 4 hours separation between the first and the second or third set of observations, such that we can monitor rapid evolution of transients. And color information is also key to distinguish from other transients, but also to do science once the counterpart is identified. Observation on the following night, or possibly even later on the third night after the merger, could truly be necessary to select a few possible candidates that could be followed up. It's just unrealistic to expect that other telescopes will take over the job of spectroscopically or photometrically classifying tens of transient for every trigger, especially if we hopefully will be able to trigger TOs for at least a handful of time, maybe tens if we're extremely lucky and there is available time. Next slide. Particularly interesting, but also particularly tricky is the case of neutron star black hole mergers. We don't truly know what to expect because no counterpart has been observed yet that we know of. So what we suggest doing here is to make the follow-up last even longer, if possible. So 1 more night compared to neutron star binary neutron star mergers, so that we can better distinguish kilonovae from neutron star black hole mergers from other type of transients. Since theoretical models tell us that probably the blue most rapid component might not be present for this type of merger. Nevertheless, a kilonova that is more rapid than most supernovae in its evolution and redder and more rapidly reddening than other transient is what we are truly looking for here. And I invite you to please go check out a lot of papers that were published during 03 in 2019, 2020, that in so many cases express the need of this monitoring a short and longer timescale. Next slide. Some target of opportunity could be interesting to be performed also for binary black hole mergers. Once again, we're exploring the unknown here, and maybe TOs will be what really help us probe the first few hours from the mergers, although maybe the following proposed time at 15 days after the merger, perhaps will be covered by the Wide Fast Deep survey. It really depends where the merger happens. Next slide. And finally, I would like to conclude by saying that with the strategies that we propose, we expect less than 1.3 or 2% of the LSST time to be used. It's surely less than that, because in case a counterpart is discovered before, for example, the second night, then we will interrupt the request for TO time. And very importantly, the TO observations will produce images that can be then incorporated into LSST. And as Peter said yesterday, this leads to a very little impact on most of the science that LSST wants to do. Almost zero for static science, and for other science cases that involve better, more time and better cadence. Peter kindly quantified with simulations that we are looking into a 1 to 3% in a difference for the metrics for the science cases. So I think it's safe to say that the impact expected from TO is really minimal. And with this, I would like to let Graham speak. Ralph, next slide, yes. And he will remind us about lensed binary neutron star mergers and counterparts.
Great. Thanks, Igor, Rafa, for a wonderful and very rich scene setting. All I really need to do then in the last few minutes is to add a layer of gravitational lensing on top of all of these exciting and observationally inexpensive opportunities that they've been outlining. So I'm talking on behalf of my colleagues in the Strong Lensing Science Collaboration that I chair along with Timo, who you heard from earlier, and a few colleagues also in Birmingham and Durham in the UK. Next slide, please. So by way of science motivation, why is it interesting to look for lensed grav waves in general and binary neutron stars and kilonovae in particular? Well, this gives us the first opportunity to look at these objects in the distant universe. In fact, at redshifts above 1. When we make the detection, then it will give us the first joint probe of both lensing and gravitational waves, which are two key predictions from general relativity. LIGO will give us an amazingly precise measurement of the time delay between the two signals. I would like to say that will give us a constraint on H0 to a precision of centimeters per second per megaparsec. Actually, I can say that, a precision, but it won't be very accurate. So we can learn a huge amount of astrophysics from that. Why not concentrate on lens binary black holes? Because there'll be more of them. It's really hard to, I could say a lot about this, it's really hard to identify candidates in real time if you're looking at the binary black holes. And who knows if they're actually detectable electromagnetically anyway. So given all of this, when is this likely to be feasible? The mid-2020s. As I'll show in a moment, LIGO will be sensitive enough to detect around 1 lensed binary neutron star per year. And I think Igor and Rafa have covered it very nicely. Why is Rubin TOOs essential? Well, it's to actually find the kilonova and to localize it. In this case, to a lens as opposed to a local host galaxy. But the analogy is very close. Hopefully, you'll see in a moment. Next slide, please. Very important point is that the lenses will be span the full range from massive isolated early type galaxies all the way through to clusters. What this means in practice is that there will be thousands and thousands of candidate lenses within the gravity-wave sky localization of a candidate lensed binary neutron star, which I think just further goes to underline the need for the wide field observations as opposed to targeted observations of possible lenses. Next slide, please. So these are the key plots. There's a lot of detail sitting behind these, but you can basically see in the left-hand panel that as we enter 05 and then go beyond that with LIGO operating at a plus sensitivity, then for reasonable neutron star mass functions, the number of lensed binary neutron star mergers available to be detected are starting to bracket 1 per year. The main uncertainty, as you can see, is on the current rates inferred by LIGO. How do these objects present to the LIGO antennae? Well, you see that in the middle panel. The arrow is showing you the lens magnification. So basically it's a vector, which is, this is just like, it's just the same as making electromagnetic sources brighter and appear to be closer. So LIGO placed these objects by and large in the mass gap between binary neutron star mergers and binary black hole mergers. We're already using that criterion to select objects for follow-up. We've done that already in 03. We're going to do it in 04. We now have a much better idea since Matt Nickel, who some of you know, has moved to Birmingham. We now have a much better idea of what we're looking for. So with his recently published, combined his recently published kilonova light curve models with my lensing calculations to make plots like these, which show you the predicted light curve for a 2017 like lensed kilonova. I've picked out the solid black curve as that is for an object that's sitting at the center of that lensed distribution in the middle panel. We probably expect these objects to be diverse. Some will be fainter, maybe many of them fainter. So to be able to detect these reliably with Rubin, we need to be getting down towards maybe up to an hour per pointing. So very careful selection of these candidates will be needed, in particular small sky localizations, please. Next slide. So literally similar theme to what you've heard earlier. These deep TOOs are the only way to unlock this science. And there are some completely new things that we can do that are related to, but at some level also quite distinct from the unlensed population. There's a direct analogy in the role of Rubin TOOs to localize to a lens as to a local host galaxy. What are we working on right now? Trying to work up a more detailed, along perhaps similar lines to what Igor was outlining just now, a bit more detailed work on what exactly does the observing strategy look like. We know how faint they are, but what does the strategy look like? It's going to be a fraction of the total TOO time. And we're keen to collaborate with people across other science collaborations to help make this work. I hope that's my last slide. Do I have another one? I've lost track. Oh, yes, there are other things that we need to work on as well, in case people want to ask about that, but I think I should stop there. Okay, thank you.
Thank you very much. Zeljko, do you think we have time for taking a few questions or listen to some feedback?
It depends on people on the call. I have no problem if we stay for another hour, but I think you'll start losing people after a while. It's 5 minutes, 6 minutes after the hour. So those who had other telecons probably left. You still have 48 people. So I would say, why don't we continue discussion? And if people have to leave, they can go to other telecoms, but those who can stay, I'm interested in learning more about this from you guys.
Great, thank you. I'm looking if anyone raises their hand and have questions. I don't see anyone at the moment.
Meg has her hand up,
Meg,
and Rachel.
Yes.
I had a quick question about the 180 seconds. And so I'm not sure if this is a question for Eric or someone in operations. Do you mean that like Ruben would take 180-second exposure, which is different from the 30 seconds normal exposures? Is that what you mean there? And if that's true, then how does that get processed? Because would you use the same templates? Does that come out as a prompt data product or something that the community would have to reduce because it wouldn't be the standard 30-second, exposure? Can you explain a little bit more what was meant by that longer exposure, or did I misunderstand what that meant?
Yes, so the longer exposure is basically we need to go deeper. So anything that would put us in that position, we will be able to collide images, whatever, but with anything that would put us in that position to get deeper.
Eric, do you have a comment to that?
I can try. It's not a super satisfying answer. The data management is supposed to be able to reconfigure our pipelines for special programs, of which TOs would be one. And so, out of hand, I can't say that, there's no guarantee, I would say, either way. I would expect with a relatively modest increase in exposure time that should be able to be processed without any particular trouble. But there probably are some limits if you went for 10 minutes or something like that, where things might start to break. And so we'd want to understand that, I think, well before the TO was triggered, so that we could prepare on the DM side appropriately.
Thank you. Rachel?
Hi, I'd like to touch on what Bob said earlier about the ongoing review and the process for actually deciding how which TOOs will be triggered and how the community can get involved in that process.
The short answer is we don't know, but developing the TOO process would certainly be a community-based endeavor. We would perhaps start with the SAC, but then there would be certainly some kind of community input to this. And then I could imagine even the COC getting involved once we had a better idea of what some of the actual use cases were and how they would go. I think what we've seen today is that the overall time impact is probably not that significant and can be handled in the current situation. But actually, when we start talking about different exposure times or wanting to observe differently and those kind of things, and plus we're concentrating on gravitational waves. There could be other TOOs that people are going to think about that would be ideally suited for Ruben. Someone mentioned the other day, a very, very large comet, and wanting to do that because it came up and it took a huge field of view. That's a different use case than what we're talking about now. So I don't have a good answer, but the answer will certainly include a broad community input.
Thank you. I would like to stress also that some of these TOOs regard a very broad community for follow-up that isn't just Ruben. There's other facilities involved as well. So there's an awful lot of technology being developed to make that happen. But coordinating such a broad community would be really helpful to know what Ruben's going to be doing and how they're going to be doing it sooner rather than later. So I don't know what the timescale is, and I hate to put pressure on the project because I know you're busy, but this is something where I think early groundwork will certainly pay off for a lot of different science.
Yeah, point well taken, Rachel. Thanks.
Thank you.
I guess one of the things I keep thinking about, and Eric does his best to allay my concerns, is the actual, when I just remember when the event in 17 went off and how much effort it took in the community to actually, find it, and so many telescopes, and even in one big telescope like Blanco, there was a lot of effort to do the search. And how well do these, when this actually happens, how well does this fit with just Ruben thinking these are just alerts and we're processing the data and sending out alerts? I mean, what else is needed, or what else might be needed? And is that going to cause us some kind of issue with other data that might be needed besides the alert packets and things like that? I think that's something that I think we really need to flesh out.
Yeah, that's something we thought about also during the development of this concept of what eventually went in the paper. Ralph can help me with this, but I think some of the requests that we have that we think can really help the community include an early release of the observing plan that we have, early release of data, because some people might also be interested in doing some data processing, not via the standard Rubin pipelines, but independently, for example, also including special type of stacking or other type of photometry. So these are among, I think, the most important requests. Ralph, would you like to add anything?
Yeah, just adding that I think that this type of science would really benefit from getting templates early on. That is the obvious thing.
Yes, thank you. I had it in my slide as a note, and I realized I actually went a bit long, so I didn't say that. So thank you for bringing it up now. A lot of one big caveat, is that we really have to do image subtraction to be able to find this type of transients in bright galaxies. So either we do it in the main footprint, which is what I hope we will be able to do. But yeah, in any case, we want deep templates to be available for that.
So Eric can comment, or Leanne, or someone else, or Angelica, but eventually, of course, we will have templates. The place where this will be really interesting is early on, when we haven't got full and complete templates around the sky and all the filters we might have wanted to do. So it'll take some thinking about how to address such a case, especially if it happens in the first year of operations.
Igor, we are beginning to lose people, so I'd like to add a quick comment that is not directly related to TOO, but since Rachel is still here and Bob in particular, several members of SCOC pointed out that yesterday there was a recommendation and emphasis on the need for coordination between Rubin and Roman and Euclid and perhaps other facilities. And we just wanted to clarify, since this is SCOC workshop, that SCOC is not charged to do this inter-project intermission coordination. That's something that happens and is happening and is at a higher level. It's led by operations leadership team, in particular Bob Blum and other in his team. We are cognizant of the need for coordination, but it's not something that SCOC is positioned to do. I just wanted to clarify this before we depart.
Yeah, that's right. And the community is going to hear soon from Leanne and her derived data products working group on some of the thinking that's been going on with respect to Rubin and Euclid sooner rather than later. They've done a lot of work. That was a community-based effort too, so some of you may already be involved in that.
Great. I don't see anyone else with the hand up. Is there any final comment or question that people want to ask, or can we wrap this up?
Graham has hand up.
Yeah, it's just a quick one. We're hearing yesterday from Timo on the static sky lensing side that in year one, prioritizing image quality in G as well as R and I was there was a strong case for that. and that had some support as well, I think, of the Galaxy Science Collaboration. Would that also be relevant to building up the good quality reference images for the grav wave EM counterpart detection more generally across the sky, Rafa and Igor? Or put another way, which filters? It'd be nice if it was G, if you agree on G as being a good priority.
I can answer by saying G is surely one of the filters that we like the most, especially if we manage to get on sky very rapidly after a merger happens, although we want to maximize usually the separation in band between fielders. So surely G would be a very good option that will help us distinguish kilonovae from other type of transients, but mainly even more if it paired with either I or Z band observations more than the other ones. So that also would be my personal preference. Raf?
Yeah, I would agree with that.
We have another hand up.
Yeah, Patricia?
Yeah, actually, hi, this is Tony. Another good reason for having a template is to actually address the main background, which is all of the transients. So in any given short exposure with LSST, you're going to have tens of thousands of transient objects, and you want to weed them out so you can find the one magic one that you're looking for. And so you need a template for that. You need a background template for that. So, you know, it really does, it's going to help a lot in order to know what objects in the field, where they are, and their past history in the time domain.
That's a good point. It's likely that we will improve our ability to follow up gravitational wave events with time. What we will be able to do after 3 years of data will probably be much better than first year of the survey. There is a great paper by Stephen Ridgway who simulated how fast we will discover variable populations. And the short of it is that after about 3 years, things will be much cleaner on sky. We will have much deeper knowledge of variable sky. I don't see any other hands, and we are already well past the top of the hour. I just would like to end by thanking you all for participating, especially today in session 4 for all the great input, and yesterday feedback from science collaborations. Thank you. It will take us some time to, as you see, to process all this great new input, but you'll be hearing from us again. We plan to have another workshop probably around next summer. So thank you again for participating, and remember, you can always get back to us in various ways, email and Slack. So stay engaged. Thank you.
Thank you, Željko.
Thank you.